3, 2, 1, action. Okay, so what we're going to do now is we're going to switch gears and we're going to talk about Zeckendorf decompositions. So there is a huge number of problems you can look at. The techniques are very similar in that I want to do this from a combinatorial perspective. It's another chance to see recurrence relations. It's another place to talk about spacings between events. I almost feel we should have made a bingo board and we should have had some key concepts and you just keep track of how often you see them in all the different talks this morning and see who's the first one to get a bingo of, we've used method of moments 5 times in a row now. All right, so here's the goals of the talk. What I love about these problems is minimal prerequisites are needed. I've actually done some stuff of this with people in elementary school. It's not that hard to define the Fibonacci numbers and start building it. Now to prove some of the theorems can be very involved. Some of the proofs are long brute force algebra. Some of the original proofs are extremely painful because they're handling very general situations. If you specialize to just the Fibonacci's, the numbers are much easier to work with, the expressions are much easier to work with, but it's not as general. So can you find a right way to generalize? The first set of papers we have involve a huge number of technical results on polynomials. We finally found a way a year ago to do it entirely elementarily. Okay. So, this slide may look familiar, but to mix it up a little bit, I have not shaded the area between A and B this time. So it's slightly different. All right, but we've seen this many times now. Probability density non-negative integrates to 1. Area between A and B is the probability under the curve. The Gaussian is going to be the big one for us. Gaussian has mean mu, variance sigma squared. So when you do the calculation, that's why these parameters have their names. Okay. So combinatorial prerequisites are pretty minimal. We need n factorial as the number of ways to order n people where order matters. N choose k n factorial over k factorial, n minus k factorial is the number of ways of choosing k people from n when order doesn't matter. And then Stirling's formula is n factorial is about n to the n e to the minus n squared of 2 pi n. Out of curiosity, how many of you have seen a proof of this? We did do a proof, but it would be interesting to remember how do we prove it in probability? We gave a lot of things that were close analogs for you. If you use like the integral test, you can get pretty close. We approximate a lot of things, but to prove, we got really good approximations to Stirling in probability. We did prove it modulo another result. It's actually a consequence of the central limit theorem if you look at a certain random variable. If you look at a Poisson random variable, you actually get Stirling's formula by the central limit theorem. It's a nice application. So this just tells you roughly how fast n factorial grows. It grows extremely rapidly. Okay. So Fibonacci numbers, we've done these before. Fn plus 1 is Fn plus Fn minus 1. We're going to start at 1 so that every number will have a unique decomposition as a sum of non-adjacent Fibonacci's. So the standard proof is the greedy algorithm. So let's take 2012. Anybody know why I'm doing 2012?
That was the year of the talk?
That was the first time I gave a talk on the subject, yes. And it's just not really worth updating the slides. So take 2012, you take the largest Fibonacci number less than or equal to it, which is 1597. Look at the remainder. Largest I can do is 377. If they were next to each other, I could have subtracted their sum. So this shows that decomposition exists. It doesn't show that it's unique. You have to do a little bit of work to get that. But if you had two decompositions that were the same, if they start off with the same Fibonacci number, well then by induction you're done because it's a smaller number. And if not, you do a little bit of work and you show that the other one can't equal the other. Okay, so I am from Boston. It's a lot of fun to try to pronounce this person's name. Lekukukuk proved in 1952 that the average number of summons in a Zeckendorf decomposition between Fn and Fn plus 1 is about n over phi squared plus 1, where phi is the golden mean. This was actually 20 years before Zeckendorf's theorem. A lot of it comes down to what journal do you publish in. And this was not published in a journal that had as wide of a range. As soon as you think of asking Zeckendorf's theorem, the proof is obvious once you've done enough math classes. You just do a greedy decomposition. And we talked earlier about why you want to localize to Fn, Fn plus 1 so that each one has the same number of candidate summons. You could go all the way from 1 to Fn because the Fibonacci number is exponentially growing. If you looked at Fn minus log n, Fn minus log n is already so much smaller than Fn that everything up to Fn minus log n is insignificant. It's a small part of the interval. Okay, so here's the central limit theorem. As n goes to infinity, the distribution of the number of summons converges to a Gaussian. So this is looking at numbers around 20, 10, 2011 for the Fibonacci numbers. The numerical simulation is really good. I really should have the show function in Mathematica so I can actually show the plot of the normal distribution at the same time as this. This was back before I figured out how to use show. Okay. What I want to do now is talk about other related questions and how you present data. So let's say we have a number m. It has a decomposition as a sum of non-adjacent Fibonacci's. We know the last index used has to be fn because we're in the interval fn and fn plus 1. Let's let k of n be the number of summons. And let's let nu mn be a spacing measure. So we're going to look at gaps between indices that are used in the decomposition. So this is very similar to what we were looking at with random matrix theory. If we have km summons, we have km minus 1 gaps. And the gap measures converge almost surely to the average gap measure, where for the Fibonacci's, its p of k is 1 over phi to the k. So it's really nice that it's converging to a geometric random variable where the parameter is the golden mean. When you're looking at anything involving the Fibonacci's, if you go 5 minutes without seeing the golden mean, you're probably doing something wrong. Yeah, it should be appearing all over the place. When you look at this plot, do you see the geometric decay going from one height to the next? How well do you see the geometric decay? Pretty well? I mean, I can see, but to me, it's hard to see that they're really going down by the correct fraction. What I've done here is I've plotted the ratio of each one divided by the previous or the one after, I forget which. And then if it was pure geometric decay, they should all be at the golden mean. And then you can see these blue dots, these ratios of adjacent terms are essentially constant. And so again, it all comes down to how do you want to present your data? Can you present your data in a clean way so someone can glance down and see what's going on? And then there's some interesting questions you can ask about fluctuations in terms of how it's going. Yes?
What do you mean by almost surely convergence?
This is just abstract probability nonsense in terms of there's different types of convergence. You can converge strongly, and if you don't converge strongly, you might converge. Exactly. And then you can converge in distribution, you can converge in probability. Some of these phrases actually mean the same as other ones. There's 4 standard types of convergence that you can do. Probabilists often get very excited about which type of convergence. Not surprisingly, strong convergence is better than weak convergence. Sometimes you need to assume additional things.
It's like almost everywhere.
So a lot of these are all related. And you know, they have different names, which makes it such a pain to figure out, you know, is this almost everywhere? Is that the same as strong, or is it slightly different? What's weak versus... I always forget which one is which. I always have to just look it up when I'm proving a paper. All right, so now which convergence did I show? Some people get very excited about trying to prove the strongest possible convergence with the weakest possible assumptions. That's not me. To me, I care about the interesting behavior. I don't care about the rate of convergence so much in something like this. But it's definitely something that one can look at. You could talk a little bit about what's going on at the end. This is, again, the effects of small. We don't have that many terms. You were only around 10 to the, that's probably a typo, that should probably be 2,000. So the gaps between the summons is not going to be too large. So what's going on here, we don't have that many data points. And when you don't have that many data points, having one extra observation makes a huge impact. Any baseball fans here? Okay, good. So in 2004, the Red Sox became the first team in baseball history to come back down 3-0 in a best-of-7 series. Is this surprising? Why might it be hard for a team to come back down 3-0?
Well, you assume first off, even if teams are even, it's 1 in 16.
So the teams are even, it's 1 in 16.
But you assume any team that goes up 3-0 on another team is the better team.
Yeah, so this is where we get some like Bayesian theory from statistics. If you're up 3-0, there may be a reason. You might be the better team. And so the odds of winning a game may not be 1 out of 2. But they'd only been on the order of 25 times the team had gone down 3-0 in baseball. So according to theory, you would expect maybe 1.5 times the team has come back. We've observed 0. Is 0 that different from 1.5? No. Now that the Sox have done it, it's a huge change. Now it's 1 out of 26 or something like that. So you've got to be very careful with small data as to effects of fluctuations like this. So that could be something interesting to study. So another question you can look at is the longest gap. As n tends to infinity, the probability that a number has its longest gap less than or equal to f of n converges to the following. So this is one of the few times in your life where you will naturally see a double exponential. This is not a professor just trying to make sure you understand your rules of differentiation. This is the cumulative distribution function. This is the probability that it's at most f of n. So let's look at what's going on here. So let's say f of n divided by log phi is smaller than log n. Let's say it equals log n minus log n. It's smaller, but not by much. When I now look at the subtraction, I now get negative of that, so I get log. I e to that, I lose one log, and I get e to the negative log n. Well, e to the negative log n is 1 over log n. So what this is saying is, if f of n is just a little bit below the expected value of log n, the probability is essentially 0. Conversely, if this is just a little bit higher than log n, if it's log n plus log n, then I would have e to a positive log n. I exponentiate, and I would have e to the negative log n. Let me see, am I doing this right? I might have done this the wrong way. I think I might have done the wrong way. Okay, so before I did fn was a little bit lower, so this was positive. Now let's say fn is a little bit larger. So now I would have a negative value up here. E to a negative huge number is essentially 0. E to the 0 is 1. I might have said it wrong the first way. So if you're just a little bit past log n, you have 1. If you're just a little bit before, you have 0. So the probability is extremely tightly concentrated about the mean. And there are very few processes that are this tight. Okay, so I want to talk about one of my favorite problems, the cookie problem. This is another way to prove Zeckendorf's theorem. It is a much harder, more painful way of proving Zeckendorf's theorem than the greedy algorithm, but it gives you a lot more information at the end of the day. So there are many proofs of the Pythagorean formula, the Pythagorean theorem. Different proofs give you a different perspective as to what's going on. So the number of ways of dividing C cookies among P distinct people is C plus P minus 1 choose P minus 1. For those of you who've done a lot of number theory, if you've heard of Waring's problem, this is Waring's problem where the exponent is 1. And the proof goes as follows. Imagine we have C plus P minus 1 cookies in a line. Cookie Monster comes and he eats P minus 1 cookies. And how many ways can you do that? Well, I have to choose P minus 1 from C plus P minus 1. So to do it explicitly, here is 8 cookies and 5 people. Probably could do this for real if people actually want to. I'm sure I have cookies in my office. The original classic Cookie Monster emerges. He gobbles up 4 cookies. And now this is how many cookies. The first person gets 2. Second person gets 0, not their day. Next person gets 2. Next person gets 3. Last person gets 1. There's a 1-to-1 correspondence with the number of ways Cookie Monster can eat 4 cookies from 12 as there is to divide 8 cookies among 5 people. It's also called the stars and bars, but then you can't justify using money to buy a Cookie Monster. You could buy stars and bars, but that's not nearly as much fun. And so another way of interpreting this that won't get you laughed at in the math department is to say I'm trying to solve x1 plus ... plus xp equals c, where each xi is a non-negative integer. How many ways can I decompose? And for those of you who are interested in the benefit problems, you could actually be playing these games here. If I want to decompose into fragments, and I've done some work on this with some of my former thesis students, how many ways can you do that? Well, that's what we just proved. All right, let's go back to the Zeckendorf problem. Let's let P and K be the number of numbers in our interval where the Zeckendorf decomposition of n has exactly K summons. So we know we have to have the last term. We don't know about the other ones. So the largest summand is Fn. So let's say we have some decomposition. We have our indices. And we know, since they're non-adjacent, there must be a gap of length at least 2 between everything, except for the first one, which could be 1. So let's let D be the gaps between them. So D1 is I1 minus 1. Dj is Ij minus 1 minus 2. What I'm doing is I'm subtracting off what I know must be true. I know this gap must be at least 2. I know that must be at least 1. Another way of looking at it is, let's go back to the cookie problem. How do you feel about that poor person who got no cookies? Yeah, nobody seems that concerned.
I'm sympathetic if that person is me.
You're sympathetic if that person is you. Or what about maybe somebody in the PANTHers group?
Yes, I wouldn't want any of us to.
Right, right. You know, if it's somebody who's doing tropical geometry, you know, or physics, or you know, exactly, you know, something like that, no problem. But you know, one of us to have no cookies.
I'd be actually happy about it.
I cannot answer stuff like this with the camera rolling, so I will save that for later today. What you could do is you could do the cookie problem. You could say, let's put some constraint. What if everybody has to get at least one cookie? Well, then that's the same as letting xi be yi plus 1, and now you reduce the number of cookies by p. Or maybe you have somebody who's really, really special. You know, maybe we have our athletic chair, and we cannot afford to have the athletic chair injured. Or maybe we're about to play a skating competition against physics, so we can't have, you know, our key skater going down. So we want to make sure that the skater gets at least 3 cookies, and the athletic chair gets at least 2 cookies. No problem. Just say x1 must be y1 plus 3, and x2 must be y2 plus 2. It's very easy to impose minimums. It's actually extremely difficult to impose maximums. To say, you know what, you know, I don't want the athletic chair to be so fat, or the skater to be so fat that, you know, they can't run fast enough or do the double, triple axel, whatever. You know, they can have at most 2 cookies. Putting on at most constraints turn out to be much, much harder. And so now if we look at the sum of the d's, it's equal to n minus 2k plus 1 when you just take everything and the dust settles. Well, that's just the cookie problem. So how many choices do we have? It's going to be a number plus k minus 1, choose k minus 1. And so we actually have a closed form expression. How many ways are there to have a number with exactly k summons where its largest summand is fn, and no 2 summons are next to each other? Here is a closed form expression. If you really understand your binomial coefficients, you actually know that there's an identity which says if you sum these numbers, you actually get a Fibonacci number. And the Fibonacci number would be fn plus 1 minus fn, which is just fn minus 1. So everything is consistent. So the way the proof works is you show, I'm going to partition my set based on the number of summons. And the sets are clearly disjoint, because if you have exactly 5 summons, you don't have exactly 8 summons. And if I add them all together, I get the exact same count as the number of numbers there are. So they must be every number, because you have some number of summons. So it's a nice proof, and it gives you a lot more to play with now that you have this. So let's do Gaussian behavior. So I mentioned that, you know, as n goes to infinity, it converges to a Gaussian. So when I went to Kant, you know, many years ago, probably around 2000, well, this might have been 2010 actually, I said the proof just follows from Stirling's formula. And I said my students will prove this later in the summer, and I'll see how far they can generalize. So the proof isn't that bad. So we write down the density. I'm shifting things a little bit just because it makes the indices a tad nicer. This is the probability of having exactly k or k plus 1 summons. I divide by the total number of numbers, and I'm now going to fn plus 1 to fn plus 2, I think. So that's why I'm dividing by fn. And I just need to show that this is converging to a Gaussian. I use Benet's formula that the nth Fibonacci number is approximately this. There's a small error, but that error is insignificant, because that number is exponentially tending towards 0, and the golden mean is exponentially diverging to infinity. And so now I just want to calculate and just show that this converges to a Gaussian. Or better yet, I want my students to show that this converges to a Gaussian. So they do some algebra, a little bit more algebra, a little bit more algebra. At this point, they try to burn me in effigy. At this point, it's no longer in effigy. And then at the end of the day, the dust settles, and you have to be a little bit careful in a few places, but at the end of the day, it comes out and you get the Gaussian density. Sometimes when you're doing these discrete problems, there's factors of 2 that you have to play with. Maybe everything's always even, so you're going to get twice the value at the evens and 0 at the odds. I forget if something like that came into play here, but it's a long calculation, but there's really only one idea. Use Stirling's formula, expand and simplify, and know that it has to converge to a Gaussian, so that tells you how to group things. So this works, it's painful, and it uses crucially the fact that we have a closed form expression for how many numbers have exactly k summons. This is not going to work in general, but it's a good start. So here's generalizations. So for the most part, we work with what we call positive linear recurrence relations. So we have a sequence hn plus 1 is some linear combination of fixed depth. The coefficient c's are non-negative integers. And the first coefficient c1 has to be positive. It can't be 0. If it's 0, interesting things can happen, and we've got some results on that. Zeckendorf, every positive integer can be written uniquely as a sum. Lecker's theorem holds, and a central limit type theorem holds. And so it gets a little bit more involved when you leave the Fibonacci's. So before, it has it's going to be a form Cn plus d for. Am I doing Zeckendorf or am I doing variance right now? Okay, this is the average number of summons. The average number of summons is going to be linear in n, and c is going to be some constant. So for the Fibonacci's, it was 1 over phi squared plus 1. There is an explicit formula for it in terms of roots of associated polynomials to your recurrence. You can write it all down. Amazed that the students are still speaking to me all these years later. But you have explicit formulas for all of these things. You get a central limit theorem as well. Let me give you a heuristic as to why you should expect a Gaussian. Let's look at a simpler relation. Let's look at hn plus 1 is 10 times hn. This is also known as the decimal system. So I'm writing any number in decimal. So if I write it in decimal, if I want to have hn present, then my first digit is between 1 and 9, and all my other digits are between 0 and 9. All the digits but the first are equally likely to be anywhere between 0 and 9, and then the first digit is equally likely to be between 1 and 9. So if I want to count how many summons do I have in my decomposition, I'm just adding the digits. And if you look at all numbers between 10 to the n and 10 to the n plus 1, every digit but the first is equally likely to be from 0 to 9, and the first is equally likely to be from 1 to 9. I'm basically adding a bunch of independent, identically distributed random variables. What should that sum be? It should be normal. And so that's where the central limit theorem is coming into play. And the difficulty is just showing that this holds in general. So to show that it holds in general is a bit more involved. I'll get to that in a moment. Here's some other games you could play. There's a nice result that you can write every integer uniquely as a sum of plus or minus Fibonacci numbers. And if you have two terms of the same sign, they must differ in index by at least 4. And if they have opposite sign, they must differ in index by at least 3. So here is how you would write 1900 as a sum of plus minus Fibonacci's. As n goes to infinity, the expected values go to n over 10. So you would expect to then have basically 2n over 10, about 0.2n summons versus about 0.276. Are you surprised or not surprised that it takes on average fewer summons than when you just used plus signs? I'm sorry? Okay, why aren't you surprised?
With the negatives, it seems like you should get a closer approximation faster.
Yeah, so you have the advantage of you can overshoot and then you can correct and come down. It's not trivial because I'm requiring that the positive summons must now differ by at least 4. Otherwise, I would then say, well, my positive summon is just a special case, and I clearly can't do any worse when I give myself more tools at disposal. But it seems reasonable that if I can overshoot and then come back, I should be able to do better. And you can actually calculate it converges to a bivariate Gaussian. The correlation coefficient, not surprisingly, involves the golden mean. So you can look at these signed decompositions and stuff along these lines. So here's Benet's formula. How many of you have seen a proof of Benet's formula? Oh, okay. So the proof is basically the method of divine inspiration. It uses generating functions. We use these all the time. We saw these when we were talking a little bit about the Goldbach problem and writing every even number as a sum of 2 primes. So I'm going to form my function g of x as the sum of fn x to the n. Now what makes this a little bit surprising is I want to understand the Fibonacci numbers, so I'm going to form a function whose coefficients are the numbers I'm trying to understand. The only way that this can make sense is that I can somehow get a closed form expression for g of x without really knowing the fn's, and then use that to get information about the fn's. In some sense, as soon as I give you the recurrence relation in the first 2 terms of the Fibonacci's, I know everything. You may be really closely looking at the slides and noticing that I'm now looking at f1 equals f2 equals 1, so these are not the same Fibonacci numbers as the previous slide. But this way it agrees with the formula that you've probably seen in books. So now what I can do is I can write my sum, n greater than or equal to 2, and I can shift indices. And if you've ever taken a class in differential equations, this is the method of series expansions. And just play games with indices. And so if I have fn plus 1 x to the n plus 1, I replace fn with fn plus fn minus 1. This is almost fn x to the n. I can pull out an x. Here I pull out an x squared. I then shift indices again. And when I'm done, I get something that looks like this. And this is almost the same as g of x. I'm just missing the n equals 0 and 1 term. Here I'm just missing the n equals 0 term. Here I'm missing the 0, 1, and 2 terms. Well, you can add all of these back. And so when the dust settles, settle dust, there we go, we get g of x minus f1 of x minus f2 of x squared equals x times g of x minus f1 of x, f1 times x, plus x squared times g of x. What do we do now? Yeah, isolate for g of x. This is exactly what you do in Algebra 1. All that's different now is that it's a function. And so you get g of x is x over 1 minus x squared. This is almost the recurrence, this is almost the characteristic polynomial for the Fibonacci's. It's actually the polynomial for the reciprocal of the roots. It's very, very similar. And so now I have the following. You could try to expand this using the geometric series formula, but if you do that, it's going to be very painful because the terms in the denominator have different degrees. Anybody know how you expand this? Partial fractions. So there's a reason you learn partial fractions. It's usually given as the least favorite integration technique. I'm sorry? I think it's great. But when you're young and you're just taking a Calc 1 class, it's like, okay, I've got a sadistic teacher who just likes to give us painful problems. But now what I can do is I factor the denominator. And now I can use the geometric series formula for each one of these, and I'm going to get pure powers that come out. And this is where Benet's formula comes from. So it's a really nice expression. There's a lot of math we're seeing today. And so here's differentiating identities. So this is one of my favorite techniques in probability. So let's say I have a random variable, so the probability it equals 1 is a half, that it equals 2 is a fourth, 3 is 1/8. It's a nice geometric random variable with parameter 1/2. So what is the mean of x? So the mean is the sum of n times the probability of n. Well, let's look at the function 1/2 x plus 1/4 x squared plus 1/8 x cubed, etc. This is a geometric series with ratio x over 2. Okay. So now if I take the derivative, so you have to wear your engineering hat to justify taking the derivative term by term. It's not too bad here. You can justify this. And you get the following nice simple expression. And then if I plug in x equals 1, I get the expected value of x. So the idea is equalities are extremely difficult to get in mathematics. You spend a lot of work to get an equality. I feel like a salesman right now. For no additional cost, we'll throw in absolutely free, infinitely many more identities from the first identity you have. And the first 100 mathematicians get a pair of Ginsu knives. Okay, it's absolutely remarkable that once you have an identity, you can generate more identities from this. If I wanted to calculate the second moment, what would I do? So how would I get the second moment? Or at least what would be the start to get the second moment? So this is giving me the first moment. I take the derivative, I'm going to get a 1, a 2, a 3, a 4. Yeah, multiply by x and then take the derivative again. So if I multiply by x, I now restore the power here to be 2, to be 3, to be 4. And then if I take the derivative, I'll then get the second moment. And if I want to get the third moment, I then multiply by x again and take the derivative. So you can calculate all the moments by just this repeated process of differentiate, multiply by x, differentiate, multiply by x. And then the way things are normalized here, we just set x equals to 1. And then it turns out that we'll show that these converge to the moments of a Gaussian. So we've seen these moments numerous times already today. So here's what goes on. So for the Fibonacci numbers, we had something very nice. Let's let p and k be the number of numbers in the interval with exactly k summits. So there's a nice expression for this. So let's look at the number of them in the interval fn plus 1, fn plus 2. I have to have fn plus 1, and then let's say the next term is ft. T can't be n, because they have to be differing by at least 2. T could be n minus 1, it could be n minus 2, it could be n minus 3. So if I want to count how many of these numbers do I have in this interval with exactly k plus 1 summons, it's the number that have, if I take t equals n minus 1 with exactly k summons, because I lost one summon from this. Or if the largest value of t was n minus 2, it would be p n minus 2 with exactly k summons. So I can get a recurrence relation. The problem is this recurrence relation doesn't have a fixed depth. It goes all the way down to 0. Crap. There's a nice technique that allows you to handle this. Any thoughts on how we can handle this? Because I hate the fact that I have a recurrence relation that now has non-constant depth. So the solution is now, let's calculate how many numbers have exactly k plus 1 summons in the interval fn plus 1. And now it's a telescoping sum and subtract. And all that stuff cancels, and you're left with Pn plus 1, k plus 1 is Pn k plus 1 plus Pn minus 1k. You now have a recurrence relation of fixed depth. The challenge is now that it has 2 indices and not 1. So you get to do, it grows exponentially fast how much fun you have. It's a lot more fun than just working with the Fibonacci recurrence relation. And you can get a generating function for this, Pnk x to the k y to the n, and you get the following closed form expression. And then you can do partial fractions if y1 and y2 are the roots, and you get the following, and the coefficient of y of n is going to just be related to what we want. So, we now just go through differentiating identities as we talked about, and we can calculate all the different moments, and we just show that things converge. All right, well, what if we do a more general relation? So the Fibonacci's, we had the following. The more general one, it's a little bit more involved. Here's the recurrence relation generating function for the Fibonacci's. Here's the general case. And you can see now why eventually we wanted a better way of attacking the problems than going through all these polynomials. This was the first paper in the subject that really cracked this open. It appeared in one of the top journals. It was great, but it was horrible getting through all of this stuff on polynomials. Partial fraction expansion, Fibonacci's not so bad. Here's the general case, significantly more involved. But it's still the same idea, differentiating identities, method of moments. All right, so now let's turn and let's talk about gaps in the bulk. So let's say we've got a decomposition. The gaps are the difference between adjacent indices. So if I give you the following, I have a gap of length 10 and a gap of length 7. So let's let P and K be the probability that a gap in a decomposition is of length k. Doesn't matter where it is, just that it's a gap of length k. I'm implicitly assuming that things converge. Is it possible that things don't converge? Yeah. So you have to show that things converge. And so the question is, does the limit exist? And if so, what is the value? You can ask similar questions about other relations. You could ask it about binary decompositions. So if you look at a base B decomposition, you get the following. The probability of a gap of length 0 is this, and then if k is greater than 1, here's the probability it's a geometric decay. If you think about it, we're not really going to do base 1 decompositions. If you look at base 2 decompositions, your digits are only 0 and 1. You should not have the possibility of having a gap of length 0. So once you have a base of 3 or higher, then you actually have a probability. So you always want to look at math and say, is this reasonable? Does the answer look right? For the Zeckendorf, for the Fibonacci case, phi over phi minus 1 can be simplified to 1. That was not corrected there. And you get this nice geometric decay. And then the general case over here, as long as C1 is positive, we have an explicit formula for what it is. It's geometric decay once the gap is length at least 2. All right, so let me give you a quick sketch of how you would prove this for the Fibonacci's. The other cases are similar. So it all comes down to finding the right ways to do combinatorics. When you count things, you want to do two things. You want to make sure you count every object once, and you want to make sure you never count an object twice. And if you violate any one of these, you have to take into account, do inclusion, exclusion, do something along those lines. So we know the total number of gaps is approximately fn minus 1 times the average number of gaps. This is not quite the average number of gaps. This is off by a small constant, but this just gives you ballpark. This is how many gaps we have. All right, so let's let xij be the number of integers in our interval that have a gap, that have indices fi and fj in the decomposition of m, but nothing in between. So another way of looking at this is it counts how many numbers have a gap of size j minus I starting at I. So I'm counting gaps of a fixed size and a fixed starting location. So now if I want to count what's the probability I have a gap of length k, well, I just take j to be I plus k. I sum over all possible values of I. This will count how many gaps of length k do I have. And a fixed number could give me multiple gaps of length k. And then I divide by the total number of gaps, and that will give me the average number of gaps of length k. So the only difficult thing is, can I actually calculate what I plus k is? Well, let's think about what this means. How many decompositions contain a gap from fi to fi plus k? So I claim that this product is the number of choices. And so if the indices, let me try to write over here. Is it not tracking? Oh, tracked? Okay. So I want to just sketch why it's true. So here's f1, here's fn, here's fi, here's fi plus k. We have fi, we have fk, we don't have anything in between. We may or may not have f1, we know we have fn. So I want to count how many legal ways are there to fill in stuff here. Well, the number of ways to legally fill in stuff here, when I don't have f1 and I have fi, that's just the number of decompositions from a number between the interval fi plus 1. So there's fi minus 1 ways of doing this. Now over here, this is almost the same as my initial problem, except that I've shifted the indices down. But I've also now required that I have fi plus k. Over here, I didn't have to have f1. Well, if I have fi plus k, what do you know must be true? If I've chosen fi plus k, what must be true? I'm sorry? So I've chosen fi plus k. You now know something. So I was just talking about the Mother's Day Miracle game at lunch between the Red Sox and the Orioles. The Orioles scored 5 runs. What do you know about the Red Sox score in the Mother's Day Miracle?
Scored at least 6 runs. If they won.
If they won. And if they didn't win?
Scored at most 4.
Right, because baseball games can't end in a tie. The former commissioner thought that this would be a catastrophe for Western civilization and has declared no baseball game will ever end in a tie. So as soon as you know that the Orioles scored 5, you know the Sox did not score 5 by the end of the game. If I have fi plus k as a summand, what do you know must be true?
It's not equal.
Well, I know I have this summand. What else do you know? Do you know anything about any other summands?
They're all bigger. If you're in this
Right, but you know something specific. I have this as one of my summands. What do you know? It's a Zeckendorf decomposition. I don't have the one right after it. I can't have the one immediately after it. So now here's fi plus k plus 2. And this is free. Just like this was free over here. So I now just slide all of my indices down. I want this to basically slide down to f1, so I subtract I plus k plus 1. And then this would become fn minus I plus k plus 1. And that's where the product is coming from.
Before the fi, don't you also know that fi must 1?
I do, but I don't need to explicitly write that down, because I've already dealt with that in terms of counting how many legally valid ways are there to choose summands in here where I don't choose things that are adjacent. And I have fi. That's just choosing all numbers that are between fi and fi plus 1. I don't have fi minus 1, you're absolutely correct, but there's no need to be explicit and spell that out. Over here, I have to be careful because I have fi plus k, and I'm not counting the number of decompositions where I must have f1. So in order for this to reduce to something I've already done, I then have to note, okay, I don't have fi plus k plus 1, but fi plus k plus 2, no idea. That's completely free. Okay. So we'll see. How's that? Okay, there. Okay, and so just that gives you what's going on, modulo some indices and some subtraction issues as to how I'm choosing which intervals I'm looking at. And so now, if I want to calculate this sum, I basically have these products. Well, I have Benet's formula for what these are, or I can use things about generating functions. There's ways to calculate these without too much trouble, and you can get really nice answers. And so when the dust settles, you get 1 over phi to the k. You can now sketch, yes, or?
A lot simpler than the formula.
Oh, yeah. It comes out very nicely.
Yeah.
And there are formulas for products of Fibonacci's and all this stuff. There's a lot of stuff that you could quote, but you can also just do it elementarily. And the fact that for these Fibonacci numbers, once your index has some power of n, or even a log n, the golden mean term dwarfs the other term. And so it's not a bad approximation to just throw the other bit away. Okay. And then you can sketch the spacing distributions between summands in a specific M. So this one is a little bit harder. Don't really want to say too much about it right now. But just the more averaging you do, this is general philosophy, the easier the problem is. So the first thing we did is I took an interval fn to fn plus 1. I took each number. I looked at each number's Zeckendorf decomposition, and I saw how many gaps of length 2, 3, 4, 5, 6, 7. And I put them all in a big bucket. And I said, how many of these, what fraction of these are length 2? What fraction of length 3? What fraction of length 4? That's the easy problem. The harder problem is to choose an M. And now that I've chosen this M, what fraction of the gaps of this M are 2? What fraction of the gaps of this M are 3? It turns out you can prove, almost surely for almost all M, whatever probability phrase makes you happy, the convergence is there. It behaves as it does on average. This is very similar to what we saw in random matrix theory. Most things are close to the system average. But it's a lot more work now. Will everything be close to the system average? No. I could give you fn plus fn over 2 plus f5. So here's something that has just 3 summands, 2 enormous gaps. But the probability that you have something like that is extremely small. But it is there. So you can make all of this stuff work as well. I'm not going to get into the stuff on longest gaps. I will leave that as slides. So I'll just go through this just so that you can hit pause if you want. I've also emailed you all of these slides. And I will shift to some new stuff. Okay. Some work I've done with a couple of colleagues, including Professor Harris, who is now here. Dawn Nelson was an undergraduate here many years ago, but I did not start working with her until she was a professor. And so we were trying to look at other fun sequences. So here is a nice generalization of the Fibonacci, and it's coming down to decomposition rules. So we'll say an SB sequence, I have bins of length B. You can't take 2 elements from the same bin. And if you have elements from a bin, you cannot take anything from the first S bins to the left or the right. And if you think about it, the Fibonacci's are just the case where the bins have length 1 and S equals 1. You can't take anything from an adjacent bin. So here, the Kentucky sequence is SB equals 1, 2. So the first bin I have 1, 2. For the next bin, I have 3, 4. If I take anything in here, I can't use the bin here, so I have to add the number 5. Do I have to add 6 or can I get 6? So can I legally get 6? So if I have 5, I can't take anything from the bin next to it, but I could take something from the bin 2 ago. Yeah, I can just do 5 plus 1. Can I get 7, or do I have to add 7? 5 plus 2. Can I get 8? Can I do 5, 2, and 1? No, because that would be 2 things from the same bin. So I have to add 8. Can I get 9? Yep. 8 plus 1. Can I get 10? Can I get 11? No, because if I do 8 plus 3, they're in adjacent bins. So I have to add 11. And then you see a little bit, the next one is 16. Next one is 21. etc., etc., etc. Do you notice any patterns?
A lot of powers of 2.
A lot of powers of 2. 2, 4, 8, 16, 32, 64, 120. Okay, so there's interesting patterns of 2. Given the fact that it's gone down this far, it's probably powers of 2, or maybe Professor Miller is having even more fun with these lectures. The other one, the more interesting one, is the smaller numbers in each interval. So it does turn out that a2n is just 2 to the n, and a2n plus 1 has a very nice explicit formula. And you have a nice recurrence relation. And what's interesting here is the leading coefficient is not 1. It's not an plus 1 is something an plus 1 is 0 an plus something an minus 1. And it turns out that when you have 0 as a leading coefficient, interesting things can happen.
Is there a reason why they're called Kentucky?
There is a reason why they're called Kentucky. And so I'm going to be a little bit careful because this is being recorded. We have nothing against the great state of Kentucky. Some of my favorite colleagues are from Kentucky. One of the people in this group is from Kentucky. And people sometimes erroneously associate a certain non-forking of family trees to various parts of the country. Any Jeff Foxworthy fans? If your family tree doesn't fork. So one of the people in the group was from Kentucky, and the comments were, when this was being done, oh, okay, it's like you can't marry your siblings or your first cousin, but your second cousin's up fair game. So the reason it's called Kentucky is which marriages are allowed or not allowed. Okay. So you can do similar stuff on Gaussian behavior, and again, you were able to prove Gaussian behavior in something like this. You can plot the distribution of gaps. Does that look different than before? Is that the same geometric decay? It's not geometric decay anymore. It's actually the superposition of two geometric decays. There's an even versus odd parity issue going on here. And if you break it up, everything then becomes very nice. But again, one of the things is, just learning lessons that will serve you in almost anything you do. Try to split the data. When we were doing L functions and talking about we could split the curves into even signs and odd signs, it's possible that certain things could be masked when they're together. And then when you split them up, things become better. So there was a superposition of states going on. So some of you may have seen the Fibonacci spiral. This was mostly done by myself with my daughter Kayla. My son Cameron helped a little bit. There's a beautiful math theorem that's hidden in here. How many of you have seen the math theorem that this represents? Okay, so it goes 1 by 1, 1 by 1, 2 by 2, 3 by 3, 5 by 5, 8 by 8, 13 by 13, 21 by 21, 34 by 34, and so on and so on. So it took a lot of work to make this. We had to use a lot of base plates. It was getting expensive, so we decided not to do the next round. How would you calculate the area of this rectangle?
Isn't it just 34 plus 21 times 21 plus 13?
Right, and 21 plus 13 is also known as 34.
Oh, yeah.
Right, it's 34 right here,
Yeah.
and that's 55. So the area of the rectangle, length times width. There's another way to calculate the length, the area of this rectangle. What's the other way? Add all the squares. 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared plus 13 squared plus 21 squared plus 34 squared. So the sum of the squares of the first n Fibonacci's is the nth times the nth plus first Fibonacci number. You can prove this algebraically by induction. It's very, very straightforward. But here's a geometric proof as to why it works. And here is the Fibonacci's tiling. So this leads to another thing you could look at, the Fibonacci spiral. And so we created the log cabin quilt. So basically, the only difference is you compress things so that all the boxes have length 1, and you don't keep them getting larger and larger and larger. It just makes it easier to draw them. And the rule is you can't take two objects that share a wall. So I'd start 1, 2, 3, 4, 5. Can I get 6? Yes. 4 plus 2. Can I get 7? No. Can I get 8? 5 plus 3, yes. Can I get 9? No. Can I get 10? 9 plus 1 is 10. Can I get 11? 9 plus 2 or 7 plus 4. So we see that we've lost uniqueness. Then I get 12, 16, 21, 28. Or you could maybe keep that cell empty because it causes some slight differences from that initial condition. So we have non-uniqueness. You end up getting a recurrence relation where the leading coefficient is 0 again. And there's a lot of things you could look at. You could look at, on average, how many summons do you need? What's the maximum number? I'm sorry, on average, how many decompositions do you have of a number? What's the maximum number of decompositions you can have of a number? What's the minimum? What do you get if you use the greedy algorithm? So it turns out the greedy algorithm doesn't always work, but a small tweak of the greedy algorithm works. And so if you want to look at the average number of representations, you can actually devise a recurrence relation. So dn is the number of Fibonacci quilt legal decompositions using only elements up to an. And then cn requires an to be used, bn requires an and an minus 2 to be used. And you just start playing these various games in terms of your decomposition, and you end up getting a nice recurrence relation for d. I mean, I consider that a nice recurrence relation. And you can solve, and you get that the number of decompositions on average is growing exponentially. It's not a huge number greater than 1. If this was exactly 1, then it would be constant. And that's what you have for most of these other things. This is a unique decomposition. This is a little bit larger than 1. How much of a variation can it have? We haven't looked at a lot of these things. A lot of these things are still open. If you use the greedy algorithm, you can see what fraction of the time does the greedy algorithm work. It's around 92, 93% of the time. For the remaining numbers, you have to tweak things a little bit. Future work is, this is stuff I was talking to you about generalizing to, two-dimensional systems. I was talking a little bit about, last time you could look at the Fibonacci quilt as a one-dimensional problem. And you could just say, I can't use 1 immediately before, or 2 immediately, but 2 immediately before is fine, 3 and 4 immediately before are not fine, and then anything beyond that is fine. So we call these F decompositions, where for each number n, Fn tells you which elements are not accessible. So we did the simple case in the past where Fn was a constant, or f of n was you can't use these consecutive numbers. But you could have f of n be a set-valued function, and just say, for this number n, this set of indices is no longer available, and the set could change as you go along. And so I will end with a really nice picture. So I did this in Mathematica, and this is what we were talking about last time in terms of generating the fundamental domain for SL2Z and then tiling the plane. And so here is my fundamental domain, and then I apply T, I map to here, I apply T inverse, I shift left over here, I apply S, I come down here, and then if I apply T to this, I would come here, if I apply T inverse, I'm here. And you can come up with some way to rank and order all these things. So we're going to have words, and you can define some kind of ordering in terms of which way you go. You could also look at this, instead of looking at it on the upper half plane, there's a beautiful theorem in complex analysis that allows you to map any, I want to make sure I say this correctly, any compact set that is connected, that is not the entire plane. I'm sorry, no, so it doesn't have to be compact, sorry. Any connected set that is not the entire complex plane, that is simply connected. I think I want simply connected. I can map it to the unit disk. And sometimes the maps are very simple, sometimes the maps are involved. There's actually a very nice map from the upper half plane to the unit disk. And so here's what's going on here. Here are my different regions. And over here, maybe I can find some kind of way to be spiraling around. What would the Zeckendorf series look like in this region? And you could use either one of these models and try to figure out how would you do this. This is something you can start doing immediately. Just playing a game and start writing things down. I have the code for this somewhere. My hope is that it's hidden in the paper, but if not, I can find it without too much trouble. And then we talked about the two-dimensional sequences before. Okay. Any questions on Zeckendorf stuff? All right, do you want to hit stop?